All right, so the audio is good. We are recording right now. All right, so I did finish grading the second exam, and I do apologize for the delay because I keep forgetting to do it. I really actually forget to do it. Um, it's okay. I admit to it. So it's all graded. If you spot anything wrong with your grade, because I gave you the scanned copy of your exam, the actual key to the exam, and also the explanation of how many points you get for each part. So you can open that up, maybe not during the class, okay, maybe afterwards, and then just kind of double check, make sure everything is right. If you spot something that doesn't seem right, let me know, and we'll take a look. So other than that, today, I just want to make sure that you guys are ready for the exam, okay? Which basically means I need to know, well, okay, I want to make sure that you guys understand the concepts, okay? So we can either go over like an overview of the concepts and then kind of strategize, what you can do to make the exam, final exam successful, or I can just, give myself another programming assignment, not your homework, but I can give myself another homework assignment, to kind of explain the structures and recursions and stuff like that. So, I can proceed in any direction. It's up to you guys to tell me what your preferences are. So, concrete stuff like actually me writing code, or kind of more conceptual stuff of, just going over the concepts that we have gone over up to this point and strategizing accordingly, what to do in the final exam. Your pick. Too many choices. We don't like choices. All right. Exam review. Okay. Any other requests? Nope. Okay. All right. So I can do both at the same time because the exam has been announced. So do you want me to go over the actual spring 2024 exam, or do you want to spend a little bit more time yourself just so that you can kind of try to work things out, without knowing the key? That's up to you too. Do you want me to go over spring 24 right now? Okay, we can do that. So let's do that. So yesterday I did something, that's kind of interesting. I think I shared with some people in my 440 class, but not generally speaking. Um, I gave my key of the swap homework assignment to ChatGPT, the little tutor bot that I made, and ask it, okay, can you simulate the execution of this TTP ASM program? It was able to do it. It was able to show the end result of the 7 and the 3, exchanging places as local variables of main. But it went beyond that. It went beyond that to confirm that it looks like your TTP ASM code is doing what the C program is supposed to do. I didn't even ask it. And it was able to make that association go like, oh, I think you got it down. So, and then later on in my Monday, Wednesday class, one of the students said, well, I turned in my code to your chatbot and it said it's all good, but now you tell me that it's not good. I go like, that's okay. Maybe the chatbot is wrong. Okay. So when I was in my office, I turned in that student's program, which I saw manually. I could see some flaws. It's okay for the most part, but there were a few flaws, and I've turned that into ChatGPT along with the C code. Like, this is the C code, this is the implementation in TTP ASM. You know, is it good? Okay, so I'm not even telling ChatGPT that it is not entirely correct. So I let ChatGPT to figure it out, and it was able to spot every single thing that was wrong with the program. And you have to understand that there's no general knowledge of TTP because that's text toy processor. Okay, only this class of this college of the entire world makes use of that architecture. And yet, just by uploading a few documents that all of you have access to, ChatGPT was able to apply all that knowledge and analyze an implementation of a C program and go like, no, I think there's something wrong over here, and there's also something wrong over here, and it was able to explain what was wrong and how to fix it. Yeah. So I find that I was actually surprised by how much the chatbot was able to do. So I just want to share with you guys. It's like, that's kind of fun, interesting. All right, so I'm gonna open this up, okay, and it's just a PDF. So at the end of the entire thing is the actual C program. Okay, so this is the actual C program. So we'll focus on the C program first, because unless we know what the C program is doing, there's no sense in talking about how to implement it. All right, so we have a structure called R in this case. It has a member called PN, which is a pointer to a struct R. It also has a different pointer called PV, which is a pointer to a value. It points to an unsigned A-bit integer. So that's how the structure R is defined. We have a program or function called flip run. It returns the pointer to an unsigned A-bit integer. It requires two parameters. One is a pointer to a struct R. The other one is an unsigned A-bit integer, which is remaining. Inside, there is a local variable, which is not a pointer, but an actual struct R. Okay, so this is kind of important because how do we declare a local variable that is a structure? So we'll take a look at this program. And I did a lot of bad things in this particular program because I made a lot of return statements inside a multi-branch conditional statement. So generally speaking, I do not do that. But in this case, I kind of had to do it because otherwise the program gets too long and it won't fit in the 256 bytes of RAM. And the main itself is, it has an array of array size. In this case, it is 3. Um, we have a structure. Okay, this is a local variable that is a structure. So first is not a pointer to a structure, it is a structure itself. The array was initialized in the code here. There are no global variables in this particular program. So a bracket 0 is 1, a bracket 1 is 4, a bracket 2 is 5. And then I initialized the members of first. So, the PV of first is pointing to the first element of A, the array, and then PN is pointing to null, and then PV is going to get the return value of flipped run, and it is using this kind of complicated thing to pass to the arguments. All right, so at this point, there are two ways to proceed, and you guys get to choose again. This is kind of one of those, choose your own path, adventure games. Remember those things, they used to exist as a book too. When we were still killing trees, to make prints, to make books, you we have one of those. We had those. So do you want me to implement this program from scratch, or do you want me to go over the assembly code and just kind of check the correctness and spot errors in the assembly code? Hmm? Sorry? From scratch. Okay, so I got one person saying from scratch. What about the rest of the class? From scratch, okay? So, okay, either way is fine. Okay, so we can do it from scratch, okay? I actually prefer to do it from scratch. Then we can look at the actual implementation and find out what's wrong with it, okay? So I think that works too. All right, so we'll do it from scratch then. So that means I need to be able to see both the C code and the assembly code at the same time. I still have this file, so I can still retrieve that, and then work on it that way. Okay, so we'll go ahead and do that. There we go. Oh, it's opening on the wrong window. There we go. All right, this is me, working out a randomized, quote unquote, randomized, priority assignment to, how professors, sign up for classes, because, I don't want to use seniority alone to determine, who gets to choose classes first. So I was working out a particular way so that it's kind of randomized, but it's not like really just random. It is, based on permutations and prime numbers and mods and stuff like that. Okay, just to kind of let you know what you're looking at right here. Not that it is too relevant. All right, so we're going to go back to the temp folder, and I will copy that file over here. So that's from my other account, CISP 310 1243 and we'll copy it over here as fx.c just so that it's easier to type. Now we can look at the C code on the left-hand side and the assembly code implementation on the right-hand side. Okay, just as usual. All right, so we'll go ahead and do the kind of the brainless type coding first. So we have a no op. We initialize the stack pointer to 0, which is actually 256 in this case. But since we cannot represent 256 in A bits, it becomes a 0 because of the mod 256 thing. Then A is initialized to the return address, and then we push it on the stack like so, and then do a JMP to main, and then we do a halt instruction right after that. So fairly typical stuff that we do, at this point of this class. We treat main as just a regular, function. And then we declare, we have to define labels so that we can find members of a struct R. Okay, so that's how we can do this. So P underscore Pn is defined to be 0 because it is the first member of struct R. And then P underscore PV is R underscore PN 1 plus because it is 1 byte after the offset to PN as a member. And then we have the size. And in this particular program, the size is actually super important. So that means we have to make sure that we calculate that correctly. Okay. So this is all proper. Okay. So we know the offset to get to each individual member of a struct R, and we also know the size of a struct R, which is really just 2 in this case. So I will do this program in a gradual fashion. Or okay, you guys get to choose again. Do you want me to finish the implementation of the entire program, or do you want to do it in smaller steps? You get to choose a lot of things. Too many choices. Don't give me choices. We just got the election done. I have done my choices already for the whole year. Okay, which way do you want to go? Do you want me to implement the program gradually? Gradually. Okay, I see some gradually. Okay, I see a few nods. Okay, so it doesn't look like somebody has a very strong objection of implementing this program gradually. So if that is the case, okay, but this is kind of important because I think you should probably do the same with your last program, which is the traverse program, is to do it gradually. So that means the first thing I need to do is to implement main first before I can even have anything to use to pass to the function. So in this case, array size is just defined to be 3, and then main has an entry point here. It has 2 local variables. Okay, one is A, which is an array. The other one is first, which is a struct R. So we'll declare A first. Okay, this is our usual order. The first local variable has the lowest address in the frame. So main A just has an offset of 0 because it's the first local variable. And then we have main underscore first. So now it is getting a little bit tricky because how many bytes is A going to take? So it is going to take array size. Okay, that's the number of elements. So technically speaking, it is good for me to do the multiplication of 1 before we add it to main A. In other words, this expression here, it is in postfix notation. So this is basically saying array size times 1, and then whatever that product turns out to be, we add that to main A. Okay, that becomes the offset to find local variable first. So the 1 times 1 thing is like, okay, why do we have to do a multiplication by 1? Because the size of each element of the array is 1 byte. That is the significance of the times 1. It is telling me to confirm that each element of the array has a certain size, and in this case, that size is 1. Is that okay? Does everybody understand the significance of the times 1? Because from the algebra perspective, it's like, why do you even bother doing it? But from the perspective of programming and understanding how many bytes we need to allocate for the array, it does have that significance. So after that, that's all. Okay, so we have to look at the local variable size. So that would be main first, which is the offset to find the local variable called first. But we also have to kind of add the size of first. So it is not a 1 plus anymore because we typically do a 1 plus because a lot of our local variables are unsigned AB integers. So that's why they're only 1 byte wide. But in this case, it is a structure. So that means it is R underscore size. That label defines the size of a struct R. So we have to add that much to the offset of first in order to find out the total number of bytes we need to allocate for local variables. Is that part okay? Okay. So now we have everything, main underscore LVS is the one thing that I really need in order to allocate the space for the local variables. So because now I can do a LDI, I can use register B, main LVS, subtract that much from the stack pointer, and then later on, I can do the opposite to deallocate. And then after I deallocate the local variables, then the stack pointer should point back to whatever it was pointing to before the allocation. Can someone tell me what the stack pointer is pointing to at the entry point of main before I allocate for the local variables? The return address from main back to the entry point. Yes. So how do we know that? Okay, which part of the lecture and the notes is mentioning that? Because I want to help you locate the material that you need to study and to make sure that you understand. Is the caller-callee agreement. Okay, according to the caller-callee agreement, the very last item that the caller has to push is the return address. And because the stack that we are using here has two conventions that are important. One, it is a downward growing stack, which means as we push more items, the stack pointer goes lower and lower. That's one. The second one is the stack pointer always points to the very last item that was pushed or allocated. Okay, so both of these are important, things to remember because stack can be upward growing and it can also just point to the next location. Okay, if I were to push another thing, where would that be? So the convention that we use in this class are important to kind of make sure that we understand. Okay, which also means you can make a checklist of those things. Okay, you can make a checklist to make sure that we are using the stack according to the caller-callee agreement. For every item, for every specification in the caller-callee agreement, you can have a checklist. You go like, okay, have I checked that we are following this particular rule when I'm calling a function? Am I following these rules when I'm returning back to the caller? And so on and so forth. Okay, so I can make mistakes. Okay, in other words, I can omit certain things and not really see a certain flaw because I forgot. Not because I don't understand, but sometimes I just don't remember. So having a checklist is super helpful because then you have a list to go over. It's like, okay, is this item checked? Yep. Is this item checked? Yes, and so on. So where you create your checklist is going to be the caller-callee specification. Okay. So that's my tip. Okay. That is me helping you to strategize what to do in the final exam. You can bring anything that is printed or handwritten, okay, and photocopies thereof. So if you say, okay, I'm going to have a checklist, but I'm not sure how many callers and callees there will be in this code, bring a few of those templates, okay? Every time you have a call, you have a separate checklist, okay? Um, so we'll move on to the implementation of control structure and stuff like that later on, but you can have additional checklists for those things too. All right, so after we deallocate all the local variables, the stack pointer points back to the return address, which means it is time to pop the return address into a register. So that would be LDBD, increment D, and then JMPB. So the JMPB is just making use of the return address in order to go back to the caller so the caller can continue its execution. All right, so this is a template, okay, a general template that I tend to use when I'm writing code. So now at this point on line 23 in the assembly code, we have the stack already fully allocated. So that means I can now start to implement the individual statements. The first one is to assign a 1 to a bracket 0. So how do we do that? The right-hand side is super easy. It's just 1. So I'm going to do LDI A and just 1. And this is my right-hand side. And then the left-hand side is um, the first element of A, and A is a local variable. So now the question is, how do we get to the address of the first element of an array that is a local variable? Well, I think we need to get to the address of the entire array first. Okay, regardless of which element we want to access, I think we need to get to the base or the start address of the entire array. Well, it is a local variable, which means the only way I can get to it is to think of it in terms of the offset number of bytes from the base of a frame. So I just mentioned the name of a frame, okay, the word frame. What is the frame of a function call? What does it consist of? It consists of, okay, what is the purpose? Okay, we asked the why, the what, and the how. So in this case, I'm going to answer the why first. Why do we have a frame? The frame provides the context for a function to operate. Specifically, it provides the local variables and also the parameters. But since the return address is also kind of sandwiched between the parameters and also the local variables, so the return address is also a part of the frame. So the labels that we have, on line 16 to line 17, only two of those are the offsets from the base of a frame to where we can find those particular local variables. So that means in this case, I need to start with that. Okay, I need to start with where we can find array A, as an offset from where the frame is. But that's just an offset. It is not an address by itself. So to turn an offset into an address, I need to add the offset to the base of the frame. But who is keeping track of the base of the frame? In this case, it's the stack pointer. Okay, the stack pointer is currently pointing to the base of the frame, which means to calculate the address of array A, I can just add the stack pointer to the offset. So now I have the address of array A. Is that okay? But I only need the first element or element 0. Okay, so that means, kind of technically, this is what I'm really doing, because the first element of an array is at the very beginning of the array, which means the offset of the first element of an array from the beginning of the array is 0. Does that make sense? Okay. All right. So now we can do the store. Okay. SD B is the address, A is the constant. So now for the next one, if I look at this code here, and if I just need to implement the same effect, but not necessarily, re-indexing and everything like that, I can just go like, hey, I already have the address of the first element. The next element is just going to be right next to it. So now I can go like, we'll just go ahead and shortcut the whole thing and STBA again. And then we can increment B one more time, LDIA with 5, STBA one more time. Okay, so I'm going to pause right here and say, okay, maybe I should debug the program. Obviously, in the final exam, you're not going to do this, okay, because you are going to do everything on paper, and there's no way you can run the actual code, okay? So you're not going to do it in the final exam. But when you're working on your traverse program, okay, you can always implement a part of something, put a halt instruction, run it, and just to see whether what you expect to happen is actually happening. Okay, so that's what I'm doing right now. But in order to know whether the program is working correctly or not, the one thing I need to do right now is okay, let me go back to, oh, up here. Nope. Oh, I need to go back to the share folder because I'm going to create a spreadsheet for today just so that I can graphically display, the layout of the frame. So we go back to shared and then create a spreadsheet for today with the same name, with today's date as the name of the spreadsheet. So that would be 2024 1205, I think. Yep. All right. So typically, we just have 255, and then this location is whatever that is minus one, and then we're just gonna do like that, and then we have decimal to hexadecimal, whatever is in column A, so that we have a hexadecimal representation of the addresses. Okay, make these two kind of shrink a little bit. This location is used as a return address. Okay, so it's a return address from main to the entry code. Um, so the first available location for local variables would be FE. So now I have to think about, okay, but how do we make use of the stack space for the local variables? So now we switch back to the assembly code and just kind of examine, what we need in the C code. Array A needs 3 bytes, and then R itself needs 2 bytes. So there's a total of 5. Okay, so now we look at 5 bytes here and say, okay, these 5 bytes together would be the local variables. So I'm gonna just use a little bit of color coding, okay, just so that it stands out a little bit easier for us to kind of focus on that. Out of the 5 bytes, the first 3 bytes belong to array A because it is the first local variable declared, and then the other 2 would belong to the local variable called first. So that means if I need to label this particular byte here, it would be A bracket 0 of main. This would be the next one, which is A bracket 1 of main. This would be the next one, which is A bracket 2 of main. This will belong to the local variable called first, but it would also be the first member of that structure, which is P, is it PN first? Okay. And then this would be the next one, which is PV. So that's how the memory is laid out. Okay, the absolute address, from column A or column B is not super duper important. What is actually more important is how they are relative to each other. So collectively, these 6 bytes, okay, these 6 bytes collectively is the frame of main because it provides all the local variables. It has the return address. And since main was not called with any arguments, so we don't have any space for the parameters. Is that part okay? All right. So that with the allocation done, register D, which is our stack pointer, is pointing at the base or the bottom of the entire frame. So now in order to get to each individual item, I just have to add the offset of the individual item. And if I need to access a particular element in the array, I just have to know, how many bytes off from the beginning of the array can I find the element. Okay, and in this case, it's fairly easy because it's an array of bytes. Are we good so far? Okay, so using this particular picture, we know the 1 should be stored over here, the 4 should be stored over here, and then the 5 should be stored over here. The return address, I can actually memorize what it is supposed to be because the entry code stays kind of the same for a lot of the sample programs. It's supposed to be 09. So I should confirm that there are memory write operations to these individual locations, FF, FC, FB, FA, with those specific values. Okay, so that's a good time for me to check. Okay, so I go back to my code, make sure I save because I tend to forget to save the code before I run it. And then we go back and just run it. fx.ttp-asm. And then I have to open the assembler too, which I think I have over here. I just need to drag that thing over to here. There we go. All right. So this is all done. Location FF, got a value of 09. Location FB, okay, go back here. Location FA got a value of 01. FB got a value of 04. FC got a value of 05. And I believe all of these are according to plan. So that's, from the perspective of writing your traverse function, even though right now we are not really doing much with structures, but the approach is like this, right? You write a few lines of code, you think, okay, I think I got this right, okay, and then you try to confirm it. Now, recursion is a little bit harder to confirm, and that's why the first thing I wanted you guys to do is not even to worry about the recursion. Okay, take out the recursive call, just implement the two statements sandwiched between the recursive call, because those have a fairly static, effect on the stack, and you can easily observe that. So start with things that are easy to observe and easy to debug. All right, so now that we know this part is done, I can go back to my source code, and if you have, if you're using revision control, oh, this is the wrong one right here. Okay, let me get out of this one first. That's the swap homework assignment. Okay, so now that we know this part is done right, we can now remove the halt instruction and just kind of move on. So we want the address of the first element of array A to be stored to member PV of the structure, local variable structure called first. So it looks kind of complicated, but what we do is we serialize, okay? We turn this into something like, okay, in order to do this, we need this first. So let's not worry about the earlier part, okay? Focus on what we need first. And then in order to do that, we need to do this first too. So you have to figure out the whole dependency thing, which means, I'm not going to be concerned about the assignment operation until I know how to compute the right-hand side. Okay, so let's focus on the right-hand side. The right-hand side says, I need to know the address of the first element of A. I think we know how to do that already because that's how we got the one to store to element 0 of array A. So we just have to do something like that. Okay, so we'll go ahead and say LDI. We can use register A or B this time again because none of those is saved. None of them needs to be saved. So I will do it with A. I'll do that with register A, main underscore A. That's the offset. Now we have the address. And this offset, we can also just kind of do a 0 plus to emphasize that it is referring to the first element. So without the 0 plus, the code is still right. Okay, so I'm not going to mark anything wrong. If you say, okay, it's just not really useful to add a 0 to something, fine, don't add a 0. But from the perspective of, oh, we are emphasizing that we are dealing with element 0 of array A, it does have some significance. All right, so now we have the address, and that's it. I don't need to dereference, okay? Because the right-hand side specifically said, I just need the address of element 0 of A. I don't need to know the value at that address. So there's no LD, no store, because I don't need to dereference at this point. So that is important because in C and C++, to take the address of seems like it's more complicated because you need an operator to get to the address of something. But when you implement it in assembly code, you always have to get to the address before you can get to the content. So that's why you kind of have to overcome that notational um, implication that getting the address is harder than getting to the value because in assembly code, you always have to get to the address before you can get to the value. Okay, so now we have to look at the left-hand side. The left-hand side specifies that we want to store to member PV of the local variables first, which is by itself a structure. Okay, so I'm not sure whether we have specifically talked about how to access a member of a local variable that is a structure, but we have talked about the individual pieces already. So we know how to get to the address of a local variable. Yes, we know how to get to the address of a member. If I know where the structure is, I can get to the address of a member of a structure. So we have talked about those two things individually, and this is just a different way to combine those two elemental concepts. So in this case, we need to get to the address of the local variable first. So we just put it into the offset here. This is the address. So register B now has the address of local variable first, which is itself a structure. So that means register B has the address of the structure already. So now that we want to access the member, which is what PV in this case. So you can do it in this way. Okay, you can put it into register C and say, okay, what is the offset of member PV from the beginning of a struct R? Okay, that is the job of this particular label. And then you can just add those two together. Which way you add is not really important because we just need the sum. So this is one way to do it. But when you look at this code, it goes like, it doesn't look very optimized, okay? Because it seems like we're just adding stuff to register B in a sequence without any dereference in between and stuff like that. So that means in this case, I could also just put the addition over here. It would have accomplished exactly the same thing. So this trick you cannot do if you are accessing a member if you're trying to specify the address of a member of a structure that is pointed to by a local variable or parameter. In that case, you need to dereference first, which means you cannot just stack the adding in when you specify the offset. Okay, but in this case, because first itself is a structure, it is not a pointer, so I can combine the addition into one single thing. Is that okay? So for things that you're not really 100% sure, you might want to jot down some notes. Okay, just go like, okay, I'm not really sure about this part. Let me try to figure that out later. Okay, and if you cannot, figure it out, come to my office hour, and I'll be more than happy to talk about it. Okay, so I claim that register B now has the address of member PV of the local variable first, which is a structure. So now I'm ready for a store because register B has the address of the left-hand side. Register A has the uh, value of the right-hand side. So I can now do a store B to A. So let's just say that I wasn't sure about line 38 is a more optimized way of getting things done. So I'm going to put a halt instruction here just to make sure that I am going to store the address of the first element of array A to member PV of the local variable first. Okay, so I'm going to have to go back to my diagram and say, okay, how are we going to change this diagram? The address of the first member of array A is FA, and I'm going to store that to, okay, first of all, I have to double check the ordering of the structure, because if that is wrong, then all bets are off. So PN is the first one. Okay, so PN is the first one, and PN is the first one. Okay, very good. So that means your PV as a member of first should now have a value of FA. In other words, this is the update that I should see when I trace this program again. So whether the code actually get it done correctly or not, I'm not sure. Okay, let's just assume that I'm not sure. But I think according to the C code, this is what it should do. Are we okay here? Because there are two parts to the whole thing. One is looking at the C code and know what memory location should be changed how. Okay, the second part is how do we do it in assembly code? So those are two different parts. The first part relies on two things that are super important. One is what you have learned in CISP 360. Okay, that's understanding the C statements and stuff like that. The second part is the convention that we use in this class. How do we allocate local variables? Okay, how do we define the offsets to members of a structure? This is how we do it, and so on and so forth. So there are two parts to just understanding how the memory locations are allocated and changed, and then to implement it using TTP ASM instructions is the other part. Okay, so we will focus on what is the right thing to do, and then we'll check whether the code actually gets it done or not. Is that part okay? Because the distinction of what I just said is important in the debugging process because you need to know what is supposed to have happened according to the C code. Then you run your code to see if your code accomplishes what you think it should do. So those are two separate steps. You can get one right and get the other one wrong, okay? But that's possible. So now I'm going to go back and just run this code to make sure that I did not make a mistake, conceptual mistake. All right, so it's all done. Okay, there we go. So now we just move down here and look at the last update. And I didn't. Oh, did I save the file? Probably did not. Okay, let me check. I think I forgot to save the file again. Control G. Yep, modified but not saved. Okay, fine. There are two favorite mistakes that I make. One is forgetting to increment, or do, what move to the next item in a loop. So I end up with infinite loops. And the second one is forgetting to save the file before I test run it again. All right, so now we get back to this code, and we are storing FA to location FE, storing FA to location FE. So we got that. So we still doing okay so far in terms of the approach of how to write your code. Okay, all right. So now we can move on. Okay, if you use revision control, it's super helpful too, because every time you confirm the program is working up to a certain point, you can check it in or just it's called commit in Git. Okay, so you can commit so that you have a saved version of the program. At least it's running up to this point. All right, so now we can work with the next line of C code, which is line 37. That one is pretty easy, okay, because A is just 0 itself. And then to access to store to member PN instead of PV, I think we can just kind of copy and paste the code a little bit here. Okay, now copy and paste by itself is, oh, yes, I can do a copy and paste. So that would be from line 38 to line 40, copy to the current location. But I have to remember to change the name of the member, which is PN this time. And that should accomplish storing the 0 to PN as a member, which means by this time, if I put a halt instruction here, I should end up with a 0, 0 stored here. So I'm going to double check that. Okay, as simple as it seems, okay, I'm going to check it because it doesn't cost a whole lot of time just to double check it. But the benefit of checking that your program is working gradually instead of making the assumption of, oh, I know this code is going to work, you know, the benefit is huge because if you make an assumption that the program is going to work, even for very simple things, and you make a very simple mistake and it's not working, then your program doesn't work later on and you have no idea why it is not working later on. So it's good to double check things, just kind of gradually make sure that, oh, I made the same mistake again, I forgot to save the file first. All right, there we go. That's the one single reason, that an ID is a good idea. All right, so I put a 0, 0 into location FD, which is also according to plan. Okay, so everything is good up to this point. All right, so now we can move on to the actual C code that looks kind of icky, okay, because it's a function call that has a super complicated, or what looks to be a super complicated argument. So we'll go ahead and check out how to do this. First of all, do we know how to do this in C? Okay, don't worry about assembly language programming, just work on this in C first. What do I need to do first? Well, according to the parentheses, I think the first thing we need to do is to figure out what is PV as a pointer minus the address of the first element of A. Okay, so we'll just go ahead and do it. Okay, so it is important to understand that we are referring to the value of the member PV, but not the address of PV as a member of the structure. All right, so first thing first, okay, we'll just go ahead and specify this thing, okay? So I'll even put a comment here because otherwise I cannot keep track of which block of code is doing what. So this is LDI. I need to get to the structure first. So and to get to that, I need to get to the offset first. Then I get to the address, okay? All right, very good. And I need to get to the member. But in this case, I can do the same trick as last time. I can add the offset to the member when I'm also just specifying the offset to the entire structure itself because we're not dealing with a pointer in between. So at this point, we have the address of PV as a member of the local variable first of main. But this code here specifies that we are subtracting from the value of the member PV, not the address. So I need one dereference. Okay, so I'm just going to pause here and see if there are any questions about when do we need a dereference and when do we not need a dereference. If you have the address and what you need is the value, you need a dereference. But there are times where you are really just trying to specify the address, then you don't want to have a dereference because the address is what you need for that particular situation. But in this case, I don't see the address of, I don't see an ampersand in front of the first, so that means we need the value. All right. So that's one thing I need to do. One thing I need for the subtraction. The second thing I need for the subtraction is the address of the first member of the array A, which is a local variable. Okay, so I'm going to do about the same thing. Okay, this is main. A is the offset, and I can do the same trick here because because main A itself is already the offset to the entire array, and I need to specify the address of the first element. So 0 plus is already enough to do the indexing. So I add BD. Yep. Oh, right, you're correct. Forgot about the plus here. Thank you. Good job. I did forget. Then the program would have not worked in this case because PV is not the first member. It would have put it into the first member instead. So that would be wrong. The program would not have worked. All right. So now we have the second thing, but once again, but this time I need the address. So that means I don't want to do a dereference. Now I'm ready to do the subtraction. So the subtraction is always subtracting uh, the second operand is subtracted from the first operand. So in this case, it would be a subtract AB, and the difference is stored back into register A. All right. Well, I think we should give it a try first. Okay. So I'm going to put a halt here. But then we have to know what are we supposed to end up with in register A? What do you think? No, no, this is after the subtraction, right? So the subtraction is looking at PV, and PV is initialized to the very same thing here. So that means after this subtraction, I think we should get a 0. Okay, we should get a 0 in register A. So to check that, I'm going to run the code. Okay, so make sure we save the code and just run it. So this is the part where, how well you understand C and C++ is going to be tested. Okay, because this has almost nothing to do with assembly code. It has everything to do with how well you understand C and C++ code. Okay, so we got A being a 0. That is correct. Okay, very good. Then we can move on. All right. So what do we do with that 0? We subtract that from array size. Okay, so we can go ahead and do that. So LDI, we can use B again for array size, and then do a subtraction of BA. So that would do the subtraction between these two, which should end up with just array size in register B because A is a 0. And then we can also subtract this extra 1 from this particular sum here. So we'll do a decrement B. So that becomes my first parameter. Oh, excuse me, that my second parameter. Um, but I want to double check first, okay, and see what we should be seeing. Array size is 3. Uh, this expression in parentheses is a 0, and then we have to subtract 1 after all of that. So that means register B should be 2 right now, okay? So we'll double check it, okay? Because everything that looks kind of complicated, we say, okay, I think we figured it out. It should be a 2, but we don't know for sure until we test run it. Being able to test run programs in kind of rapid succession is called rapid prototyping, and it is something that only can be done when you have environments that can support it. Um, so we'll take a look, and B end up with a value of 2 before we get to that halt instruction, so everything is good. So now we can push it on the stack. So we will push that on the stack, push B on the stack. So that means we decrement D and then stdb. Okay. Where did we talk about this? To push the value of a register, regardless of what it is storing, what the register has. To push a register is to use decrement D and then stdb. Where did we talk about this? When we first talked about calling and returning. That was the first time we introduced the concept of a stack, which also includes the C++ notation of how to work with a stack pointer, and then later on translating into TTP ASM code. So that's where you can find the specification of how the stack is used in this context. Okay, so now we have to push the address of first on the stack. So kind of the same deal. Okay, LDI a main first, add AD. That should be the address or not. So think about what we just did. Okay, these two instructions, 61 and 62, is pushing a 2 on the stack, which means when we look at the picture of the frame is fine, not a problem, okay? But this location here is now storing a value of 0.2 because this is the second argument of the function that we're trying to call. So I'll just call this argument 2, okay? So that means the stack pointer is no longer pointing at the base of the frame. The stack pointer is now pointing to 1 byte below the base of the frame, which also means the offset to all the items of the frame are now 1 byte off. So the offset that we have already stored in the labels, the offsets are not wrong because the offsets are calculated at the base of the frame. But the stack pointer is not pointing to the base of the frame anymore. It is pointing to 1 byte below the base of the frame. So it's not like the calculations were wrong. It's just that the stack pointer is not pointing to the base of the frame. It's pointing to 1 byte below the base of the frame. So there are two ways to fix this problem. So you can either increment A right after this, okay, to adjust for the decreased stack pointer compared to the frame of the base. But this is also fixable just by adding 1 to the constant that we're loading into A. So both of these would do exactly the same thing. Okay. So we're going to assume that this works. Okay. And then we say, okay, we have to push that on the stack. Do we need to dereference before we push it? Register A. Do we need to dereference register A after line 65 before we push it on the stack? We do not, because we are supposed to be pushing the address of a local variable. So after we compute the address, that's all we need. Okay, we don't need to dereference because I don't care about the value in first at this point. I just need to know where I can find first. So now we'll do the push. Okay, decrement D, std, in this case A, and I'm gonna pause again. So you go like, not again, not another halt instruction. Yes, another halt instruction. Because until we know that you push the right things on the stack, there's no point in trying to implement the function that you're supposed to be implementing, because if it's not getting the right information to begin with, it's not going to do the right thing regardless. So we really have to confirm that we're pushing the address of first and 2 on the stack. So now we have to go back to this diagram and go like, okay, what is that supposed to be? We're supposed to push what? The location of first, which is location FD as the first argument here. And that would be just location FD. Okay. So we should see location 02, or excuse me, the value of 02 overwriting location F9, the value of FD overwriting the location F8 at this point. So go back here, make sure it's saved, go back to here, just run it again. So this part here is kind of an overlap between, helping you to understand the final exam and how to locate problems with the final exam, and also how to approach the last homework assignment, which is implementing the Traverse program. So I'm trying to explain the approach of doing things along with all the technical stuff that you need to know in order to implement the program. All right, so we'll double check. Okay, 02 is stored to location F9. Okay, that's as expected. And then we have FD overwriting location F8, FD overwriting location FD, all good. Okay, so we have just implemented the pushing of the arguments of this particular function call. Okay, and then we are now ready to push the return address, which is LDI A.6 plus document D stda. And then once we store the return address, it is time to call the function jmp I to flip run. And then when it comes back, I know that we have to increment D twice. So the reason it is important to understand why we need to increment D twice, because we have 2 bytes of argument sitting on the stack. That is the reason why we have to increment the stack pointer twice, is to deallocate the arguments. But we push 3 things on the stack. How come we are only clearing 2 of them? Can somebody tell me why? I mean, how do I know that we push 3 things on the stack? Because I can count the number of times we decrement D. 1, 2, 3. We push 3 things on the stack, but we only increment D twice to quote unquote balance the stack. What is that one last item? Exactly. The callee is responsible to pop the return address. When we use the word pop, it means to deallocate as well. It's not just to retrieve it, but we also have to deallocate. So where do we know this? Takito, where did you mention something like that? It's part of the caller callee agreement. So that means it is also something that you can put on your checklist. Okay, if you're presented with the implementation of a function, is that function deallocating the return address? If it's not doing that, you go like, hey, you're supposed to do that. It's not checked. This box is not checked. Something is not right. Okay. All right. So now we can now move on to talk about your flip run. This program is not done yet because I'm supposed to put it back into. I have to add one first and then put it into PV. But I'm just gonna put a little to do here. This is also something you can consider doing, is simply to remind yourself, okay, I'm not quite done with this yet, but I'll come back and do it later. Okay, so we will say that only the function call is done. There is some more work to be done here. Okay, so that's just note to self. So now we can go back and implement the function itself, and that is over here. Okay, so that is flip run. Okay, so the first thing we need to do is to figure out, okay, what does this frame look like? Okay, that's always the first thing you need to know, is looking only at the C code and figure out what does the frame look like? What should I be expecting on the stack when I get to the actual first statement in the C code? Always the first thing to check. Okay, it does have one local variable. N is a local variable. So we need to say, okay, flip run, you have N as a local variable. And as the only first and last local variable, it is at an offset of 0 from the base of the frame. Okay. Now we have to say, okay, since you're the only local variable, now we can try to calculate the size of, how many bytes do we need for all the local variables. So it is flip run underscore n. And if you just look at the pattern of how we do things in this class, people would just go like, oh, 1 plus. No, it's not 1 plus, because that 1 refers to the size of the last local variable. And we usually have either a pointer or a byte as the type of a local variable. This one is not. This one is not a 1 byte thing because it is a structure. So the size of a structure has its own label, R size plus. that is how we calculate the local variable size. Because so this is important, okay? Because for people who just look at the pattern, they go like, oh, the pattern is blah 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 one plus, blah 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 one plus, and blah 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 one plus, and they would just go like, okay, one plus is good. But if you think about why we have those one plus before, and you think about, okay, the one plus is not just a pattern. There's a reason why we're adding one, and now you can adjust and go like, okay, wait, hold on a second here. What is the actual size of local variable n? It is not one. It is whatever the label r size is defined to be. Is that okay? So I'm trying to point out, things that is a common mistake, that people make. And the interesting thing is ChatGPT makes the same kind of mistakes too, because guess how ChatGPT learns? By recognizing patterns from examples. So in order to convince your ChatGPT not to make mistakes like this one, they're using a one instead of R size. Um, I ask ChatGPT, how can I make sure that you don't make this mistake when you're presenting a solution? Guess what the feedback was? Give me some examples of not using one, in the one plus. That's what it told me. So, which is really funny because computers are supposed to be very good at following strict rules. ChatGPT behaves more like a person than a computer in this case. So that is how I know what to emphasize in this class because I think some people in this class might be learning in the same style. And as a result, it is important for me to point out, no, not always one plus. Okay, you have to think about why that one is the one. So that's kind of interesting. That's what I learned from working with ChatGPT to make that tutor bot is to get the tutor bot to work correctly. I have to give it like many different examples. I cannot just explain the concept and expect it to work the first time. It cannot just say, "Oh, these are the rules. I just have to apply the rules." Okay. So now you have to think about this yourself. It's like, what kind of a learner are you? Do you learn by observing examples and try to extract a pattern out of the examples? Or do you try to understand the rules and the rationale behind the rules underneath and try to use the rules to kind of solve problems? Because those are two different types of learning styles. And guess which one is more useful in computer science, software engineering, and kind of related fields? So I'll leave that as a question to you. The way people learn can be changed. So it's not like set in stone, but being aware of how you do things now and how you want to do things when you are in your career, that is important because you can change it. But if you don't know that you need to change something, you're not going to change it because you don't know what you need to change. All right. So now it is all good. Okay. Then somebody's going to say, but Tack, wait, hold on a second here. This is a structure. Why are you just adding one in this case? Because it is not a structure. Okay, pos is a pointer to a structure, and every pointer is only 1 byte wide. Okay, so that's also important. Okay, that little asterisk symbol is super important because it is distinguishing, is pos itself a structure, or is it really just a pointer to a structure? So this is all CISP 360 concepts, okay? In other words, this class, okay, is really stress testing what you know about CISP 360. Is it a good thing or is it a bad thing? What do you think? I think it is a good thing, okay, because as much as it might sting and hurt a little bit and go like, oh, darn it, I did not really fully understand that concept. Well, at least you know now that you're not fully understanding that concept. Because do you think this is the last class that you need? This is the last class that requires a good understanding of pointers, structures, and and all that stuff? No, not even close, right? So that's why it's a good thing. Okay, stress testing at this point is actually a good thing. It may not feel good this semester, but it's a good thing. All right, so now that we have LVS, we can set up the function. So that means I need to allocate, deallocate, do the return code, the usual thing. So if you see me writing code this way, it means you might want to structure your checklist in a similar way. Okay, the entry code are the labels defined correctly. Where are my local variables? Where are the parameters? Are they at the right offset? Do they play by the rules specified by the caller-callee agreement? Okay, checkpoints. Okay, all the little check marks on your checklist. Okay, so now we do a LDI B. The reason why I use B instead of A is because A can be used to specify a return value, like in this case, but B and C are always safe to use. So that's why I use B and C usually and not register A. So flip run underscore LVS, subtract, okay, DB to allocate, and then do the opposite later on to deallocate, and then right away I can do the return code LDBD increment D JMP B, like so. Okay, so in between here, now I can do all the actual code in the function. We are now at 10:05, so now I'm giving you guys the decision earlier, okay, because I think I may not be able to finish the code by 10:20, which is now. So I'm asking, do you want me to use part of the lab time to finish this entire program, or do you want to just go like, okay, I just need to move on to finish my own Traverse program. I don't want to look at this program any further. So it's up to you. Finish it or not to finish it. Finish it. Okay. All right. All right. So now we can get to the first statement here, which is just looking at remaining. If remaining is not true, which means it's null, or 0 in this case. It's not null because it's an actual 8-bit integer. If it's a 0, then we just return the value PV, the value of PV of the structure the PPOS is pointing to. Okay, so let's go ahead and just implement the conditional statement. So this is another template that you can also turn into a checklist, which is, oh, we have a conditional statement here. What should I check when I see a conditional statement? Well, this particular conditional statement has a then, has an else, okay? So we're going to have to check to make sure that all of those components are in place. Okay, so we're going to say evaluate a condition and then do a conditional branch to the else case. Okay, so we have this is going to be if this is going to be flip run underscore if 0. Oh, actually, it is going to be else 0 because it's the first conditional statement at the top level of the function flip run. That's how I determine the name of the label. And then we're going to have the then branch over here. Then we are going to have a JMPI to the end of the conditional statement to skip over the else portion. So we have jump to flip run underscore and if 0. And then we're going to define the label flip run underscore else 0 over here. And then we have the else branch over here, and then followed by the actual end of the entire conditional statement, like so. So that is the template. Okay, the template of a conditional statement is like this. What if there's no else branch? Well, that means this is just empty. That's all. Okay. You can optimize the code a little bit, just so that you save one unconditional branch. But if you have that unconditional branch here, which is not necessary, it's not wrong. Okay, I cannot mark you wrong for that. All right, so now we have to go back and say, but what condition are we evaluating? We want to, if remaining is non-zero, we go to the else branch. Okay, so that gets a little bit complicated. We'll take a look at that. But before we can even make the conditional branch, what do I need first? I need to negate the value of, this is the logical negation of the value of remaining. Okay, I just said the value of remaining. But in assembly code, to get to the value of something, you have to get to the address first. So I need to get to the address of remaining. Remaining is a parameter, which means it is in the call frame, which means I should have a offset to get to that parameter, which I can get to immediately. Okay, so that's the first thing I need to do. Okay, so LDI, I can use register A in this case, um, flip run underscore remaining, add AD, that will get me to the address. But this time I don't see the address of over here, which means I need to get to the value. So that means I need the reference to get to the value. Okay, I have the value now. How do I get to the else case? Oh, if it is not zero. But the only conditional branch you can use that relates to a zero is a JZI. So now you have a choice. You can use a JZI to go to the then branch and then a JMPI to the else case, okay, which is actually the only way you can specify this. But I'm going to throw a wrench into this whole thing. I'm going to do a dot 2 plus and then an unconditional branch to uh, flip run underscore else 0. Okay. Then you guys go like, we have never seen anything like that. You cannot put this in the test. I can, because we have talked about this, just not in this very specific case. Okay. In other words, if you have a bunch of Lego blocks, okay, do I have to show you every single possible way to combine the Lego blocks to make every single possible thing that is makeable from Lego pieces? The answer is no. Okay, that would be unreasonable because there are so many things you can make out of Lego blocks. All I need to show you is, oh, these are special pieces. They are not square blocks, okay? They can do certain special things. I show you those special pieces, explain how each special piece is special, and show you exactly how to use one, okay, in one instance. And that will give you the idea of, oh, okay, so these things can turn, or these pieces have a hinge, or these pieces are tiny little pneumatic, thingies, okay? But how you apply that in a new design depends on what the new design is supposed to do. So in this case, I give you something that you have not seen before, okay? Because we always do it. Oh, LDIA dot 6 plus, and that's how we specify the return address. The question is, how does that work? It works by counting the number of. So now it goes back to the definition of the dot. What is the dot representing? It is the address of the opcode of the same line, right? So that means this dot is the opcode, the address of the opcode of JZI. What about the 2 plus? Well, it's postfix way of saying plus 2. So now the question is, what is 2 bytes after the opcode of the JZI instruction on line 28? What do you think? Okay, huh? After the JMPI. So I think, I think I made a mistake here. This is supposed to be a dot 4 plus, not a dot 2 plus. Okay, a dot 2 plus means it is actually not doing anything because it is just jumping to the JMPI instruction. This is supposed to be a dot 4 plus. So I do apologize. This is a dot 4 plus because 0 is here, 1 is here, 2 is here, 3 is here, 4 is right here. In other words, JZI dot 4 plus jumps right into what is supposed to be the then branch. Okay? And if you say, oh, no way, no way this is going to do that. Okay, fine. We'll put a halt instruction here. We'll test it. So we'll put the halt instruction here, and we'll put another halt instruction here. In other words, the program will halt one way or another. The question is, am I halting at the right instruction? Is that okay? All right. So based on what main is pushing on the stack, remaining is supposed to be 2. So that means not remaining is going to be false, okay? Because remaining is true, not true is false. So that means I should end up at the halt instruction on line 38. Is that okay? So right now, I'm not even finishing the implementation. I'm just testing out this really, really weird way of specifying where JZI is supposed to go. Okay, and I want to make sure that it does work. Okay, my understanding is correct. So now we just give it a test. Okay, we save the file, we give it a run, and then we go to the assembler. We go to, it's going to be one or the other of the halt instruction. This is the halt instruction on line 39. Is that the correct halt instruction? Let's check. So the line 38 is exactly where the blinky cursor is, which is what I said we should end up at. So that's how it worked. Now, there's another way to you can look at this and say, oh, okay, now I get what it's doing, which is to look at the assemble, the assemble tab of the assembler. So when you go to the assemble tab, you look up the line that contains that really kind of weird, dot 4 plus thing, which is this line here. And then you ask, what is the address that it's supposed to go to? It's supposed to go to location 15 or 15 in hexadecimal. Location 15 is exactly where the halt instruction of the then case is a, let's see, yeah, this is the then case. And then the else case, according to the command, has a halt instruction on this line here, which is line 38 or location 18. Is that okay? So once again, if you are having some doubts of, I'm not really sure I'm fully understanding this, write it down on a piece of paper so that you can kind of think about this a little bit more. Okay? Because the whole thing boils down to, do you understand what the dot notation is representing? And do you know how many bytes each instruction takes in the implementation? Everything that has an I in it takes 2 bytes. Everything else takes 1 byte. Okay? So that means LDI, JMPI, JZI, JCI, blah, 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 they all take 2 bytes. Everything else, like LD, ST, add, subtract, compare, CPR, they all take 1 byte. Okay? All right. So now that we know the conditional statement is working, we can continue with this program. Okay, so we can say um, there's a nested conditional statement here. We'll worry about that later. So we are going to say, okay, we are specifying the code for the then branch, which is simply to return PPOS, or PV member, the value of PV as a member of the structure the PPOS is pointing to. Okay, so at this point, this kind of construct should be boring because we have explained how to do this kind of expression many, many times already. Okay, so the thing is, do you know just the routine and the pattern to do it, or do you know why the way we do it works? Okay, so those are two different questions. All right, so to get to a member of a structure that the pointer is pointing to, I need to get to the pointer first. So that means PPOS is absolutely the first thing I need to get to first. So we do LDI a flip run underscore PPOS. That's the offset to the to the parameter. Add AD, that's the address of the parameter. LDA a, that's the actual value of the parameter, which is itself a pointer to a structure. So now we have the address of a structure in register A, but I'm not interested in the entire structure. I'm only interested in one of the member, which in this case is PV. So I'm going to load the offset to find PV as a member from the beginning of the structure to register B, and then add register B to register A, and then we dereference it because we are not returning the address of a member of a structure that is pointed to by a pointer. We're returning the value of that. So now we have to load LDA A to dereference it. So that will get line 12 done. It is important to understand why in this case, we cannot just do a RPV plus on line 33 because line 33 is not getting to the address of a structure, it's getting to a pointer to the structure. So that's the difference. And that's why we cannot just do a R underscore PV plus on line 33. We have to add it later on after we dereference the pointer. Is that okay? So this program illustrates those two concepts pretty clearly. How do we get to a member of a structure that is pointed to by a pointer, as opposed to getting to the member of a structure that itself is a local variable? So those two concepts are very distinct in terms of how we compute the address of the member. So if you're not fully grasping that concept right now, it's okay. But you need to make a note of that so that you remember to kind of redigest this material later on. That's what notes are for, because if you don't take notes, you're not going to remember to do it. All right, so now we are dealing with the else branch. Okay, so here's the else branch. And the else branch itself has its own conditional statement. So now you will start to see the way I define the labels to be useful, okay? Because in this case, I need another template of a conditional statement, which means I have to evaluate a condition, and then I have a conditional branch to the else case. So in this case, the else case label is going to be else 0 underscore else 0. Why? Because I like else 0? No, because we are branching to the else that is inside the else of a top level conditional statement. So the name I late blah, 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 the way I name the labels is conveying the structure of the program, and I would do it consistently in the final exam as well. So you can basically make use of that um, assumption to help you understand. So where are we in this code? Oh, we are trying to find a reason to go to the else branch of the conditional statement inside the else branch of the top level conditional statement. Okay. So that means if I don't make this conditional branch, then we have, this is the code of the then branch. Okay. And at the end of the then branch, we have to go all the way to the end of the conditional statement. So I have a JMPI to flip run underscore else 0 underscore and if 0. Because this is the end of the first conditional statement inside the else branch of the top level conditional statement. So the, the naming of the label is kind of important here. If I want to trick you guys, give you guys a real headache, I'm just going to use L1, L2, L3, L4, and so on. Then you guys go like, and then make sure everything has the same indentation level. That would be bad, okay? Because then you can look at the code in assembly and go like, I have no idea where I am or where it is supposed to correspond to in the C code. The way I'm doing it right now, it's kind of structured, okay? There's a certain structure to the whole thing. If you know how to read that structure, it's going to help you in the final exam because you know, oh, okay, this chunk of code is supposed to be that C statement over there, okay? That should help. All right. And then after that, we have the else branch. So the label of the else branch should go here. So flip run underscore else 0 as a label definition should go here. And then we have, okay, I'm going to use slightly de-indented here. So flip run underscore else 0 and if 0 should be here because that's the end of the entire nested conditional statement. So this is the else branch. All right. So I just gave you the structure of a conditional statement again. So every time you see a structure, it's like, oh, we need to have this piece over here, and then this piece over here. That's a reminder of checklist. Okay. So that means the way you apply your checklist is not linear. You're not just reading line after line after line. You're looking for things. It's like, okay, do I see a conditional branch to this label, which is the else? Okay, does that make sense? And then you see the then branch, and at the end of the then branch, do I see a unconditional branch to skip over the entire else branch? Do I see the else branch label here, right after the unconditional branch of the at the end of the then branch? And then do I see the definition of the end if label to mark the very end of the conditional statement? So those are all the key pieces of a conditional statement, structurally speaking. Is that okay? All right. So now we go back here and we say, okay, what do we do to get over to the else branch here? All right. So we look at this and go like, if remaining is 1, then we go to the then branch without any question. Okay. If remaining is not 1, then we have a second thing to check. Okay. So the way to do this is I'm just thinking whether I should use De Morgan's law. So I'm not going to use apply De Morgan's law here because that's a little bit more than what I need to talk about in this class. So what we need is to make sure that remaining is not 0, and this greater than is also not true in order to get to the else case. So that's what we're looking for. All right. So now we have to evaluate the condition. So we have to check this one first. Okay. So that's relatively easy to do because it's a LDI. Okay. LDI A1. Okay. That's just the one of the equality check. And then the other piece is the value of remaining. So we have to load flip run underscore remaining, which is the offset into register B, add BD to get to the address, and then dereference it once because we are looking at the value of remaining, not the address of remaining. And now we can do a compare. Either way is fine. Okay, compare AB, compare BA, doesn't really matter because we only care about whether it's an equal or not. So in this case, if it is an equal, we can go straight to the then branch. So we can now say, okay, we go to flip run underscore else 0 underscore then 0. Okay, and that label is not defined yet, and I can define it right here. And that would be flip run underscore else 0 then 0. And put a colon here. There we go. All right, so if I end up here, that means remaining does not equal to 1. So when I write code, I actually have to use labels or comments like this, just so that I can keep track of what does it mean to be on line 51. Oh, okay, it means remaining is not 1. So now we continue with the second part of the OR, and we ask, we have to compare these two. So when you look at this one, you go like, that doesn't seem to make a lot of sense. How can this be greater than that when this one has an obvious +1 and this one does not have the +1? What do you think of that line of reasoning? It is what it points to that I'm comparing. I'm not comparing the addresses, okay? In other words, in the C code, what I'm comparing is what PV as a member is pointing to as opposed to PV +1, what it is pointing to. So I'm not comparing the addresses, I'm comparing the content of these two addresses. Is that okay? All right. So let's go ahead and see how we can do that complicated thing, or seemingly complicated thing. All right. So that means we have to, I think, regardless, we have to get to PPOS, right? Because we are looking at member PV of PPOS regardless. So let's get to that one. So we have to do LDI. You can use register A here. Flip run underscore PPOS. Add AD. Get to the address of PPOS. And then LDAA to get to the value of PPOS. And then we have to get to the member PV of the structure that PPOS is pointing to. So I have the LDIB with R underscore PV, which is the offset to get to member PV. Add that to register A. So now register A is the address of member PV of the structure the PPOS is pointing to, finally. And, but that's just the address of. In other words, I have the address of this thing, and which is also the address of that thing over there, which is not what I really need because I need the value of the member, not the address of the member. So I need to dereference once. Okay. So now we really have PPOS points to PV in register A. I can see that you guys are starting to lose attention. Do you want me to continue or do you want me to kind of do this later? I can continue. That's not a problem. Do you guys want me to continue? Continue later? Or you can just kind of pretend that you're paying attention. Let me finish the recording, then you guys can watch the recording later. If you want to leave now, that's okay with me too. I'm just gonna talk to nobody in the class as if I'm talking to someone in the class. I'll even pause and ask, are there any questions? Just so that when you watch the video, it feels normal and natural. I can do that. It's not a problem for me. So anyone who needs to leave right now because you got other things to do, it's the end of the semester. I understand that there are other projects that you need to tend to. It's not a problem. I would not be offended, but I will go ahead and finish this. Okay. So if you want to stay with me, that's definitely okay as well. Okay. Just want to make that clear. Okay. So over here, I'm going to say one thing. Okay. Because, we, it's a long sequence. Okay. So it's good to say what register A has at this point. So register A now has PPOS points to PV, which the proper way to say that is it has the value of member PV of the structure that PPOS is pointing to. Okay, so the long version of saying this is actually super important because if you know how to say it properly, then you can figure out the dependency and then implement the whole thing to figure out how to specify the instructions to get it done. All right, so this is really useful because this one is just dereferencing that. This one is dereferencing one more than what A has. So now I have just enough registers to play with this because I can do LDBA. So now, okay, so in this case, it is kind of important to kind of note what each register has because otherwise, even I cannot keep track of all of that stuff. So now I can increment A, which is doing the +1 over here, and then we can do a LDCA. So the register C is now the dereference of PPOS points to PV, the whole thing +1. So now I have register B being the left-hand side of the original comparison, and register C being the right-hand side of the um, right-hand side of the comparison operator. So now I can actually do the compare. Okay. So in this case, I need a confirmation to go to the then branch. That would be the easier way to do things. So now I can do a CMP, blah, blah, and say that JLI, okay, is JLI? Yep, it is a JLI to the then branch, which is flip run underscore else 0 underscore then 0. Okay. So the question is, what should we use as the order between B and C? Because I know we have to compare B and C, but are we comparing B to C, like using B as the first operand, or the other way around? So we are trying to confirm that C is less than B. So CB is the correct order. Okay, because we're trying to confirm that whatever register C has is less than whatever register B has in order to go to the then branch. So if we fail all of this stuff here, then we go to the else branch. So we have to remember that we need this one to go to the actual else branch, because if we fail to find reasons to go to the then branch, we better get to the else branch. Is that okay so far? Okay. So I have just broken one of the rules of writing a whole bunch of lines without debugging it. But since we are if I keep doing it in a very very gradual way, it's going to take a lot longer. All right. So now this one has a simple thing to return. It is just returning, you know, one of the things that's already in the register. Okay, so I will let you guys figure out what am I supposed to return over here. Okay, I'll give you three choices. Am I going to return the value in register A, in register B, or in register C? Register A, very good. How do we know? Because I left behind some really useful comments. Because if I did not leave behind this comment here, I would have to go back and redo the calculation to figure out. So that means that is also a strategy that you can use in the final exam. Okay. You can use shorthand that only you understand. Okay. You don't have to make sure that I understand your shorthand. But whatever you do, you need to keep track of what is in each register. Okay. So now you can think about it. Okay. You can strategize and go like, okay, what notation makes sense to me? To me, this notation, this kind of notation makes sense. Whatever register has the value of whatever expression is specified in the C code, it makes sense to me. But it may not make sense to you, so you have to come up with your own notation. But you still need to keep track of what is in each register. How does it relate to the C code? Okay, that is the most important part, is how does it relate to the C code? All right, so that means I really have nothing to do here. Because to specify the return value is to put that value into register A, which means if register A already has the value that I need to return, I'm all done. The then branch is nothing, okay? So only the else branch has something to do now. So now I need to specify the else branch, which has something pretty ugly to do. Well, it's not quite as ugly as you think it is. And by the way, I made a mistake too. I made a mistake because register A actually does not have this thing here because of line 60. I caught myself. Okay. A is actually P pos points to PV plus 1 because of the increment A, which also means, in the then branch, I have to decrement A because of that. I'm actually surprised that I caught this one because, normally I would have forgotten about the whole thing and go like, it's okay. But for whatever strange reason, I actually went back and double checked. It's like, wait, hold on a second here. Register A does not have, P pos points to PV. It has one more than that. Yep. It is the value. It's the value because we have this dereference. Before that dereference, okay, so if I were to comment this entire thing, this would be the address of the member PV right here. So that's why, it's good to keep track of, what is in each register. Um, yep. Okay. So now we get to the else branch, and the else branch says, we have to get to PPOS PV plus 1. And since PV is still PV plus 1 right now, register A has the right hand side. Okay, if I do tricks like that, I have to remind myself that register A is already the right hand side. And now we have to specify where are we supposed to store that? We're supposed to store that to member PV of the local variable n. But variable n is a structure. So that's the important part. It is not a pointer to a structure. So now we have to go like, okay, that's how we can do that. LDI A. I cannot use A because A is already the right hand side. So B with flip run underscore n, which is the offset to local variable n. And then we do add BD. That would be the address of the structure already. Okay. And I'm supposed to add the offset of PV to the address of the structure. That means, oh, I can just add it over here. So this time I can combine the adding of the offset when I specify the offset to the local variable itself. So this is also something that you can potentially jot down, is to make sure that you understand when we can combine the adding of the offset of the member to the offset of the local variable or parameter, and when we cannot do that. Okay, so understanding that distinction is really important. It would actually help you understand C code also. Okay, so in the future, if you're taking another class in C++, this will actually help you make everything like super crystal clear because in assembly code it is very distinct. Okay, so now we have the address of where we're supposed to store that. We just go ahead and store to register B, whatever is in register A. So that takes care of line 20. Now we need to take care of line 21. I don't have any quick way to do that, so we'll just go ahead and do it the long way. LDIA with flip run ppos add AD LDAA. In other words, if you don't see ampersand, most likely you need a dereference. Okay, if you see a dereference, it means if you see the ampersand, it means you probably don't need a dereference. Okay, but it's a general rule. Okay, don't apply that blindly. Okay, always make use of that observation based on the context. Okay, so now we have ppos in register A, and we need to store that to pn of n. So we know how to do that already. So we have a LDI b flip run underscore n r pn plus add bd stba. All right, so that should accomplish line 21. And now we just have the recursive call to handle. The recursive call is not too bad. We are just pushing remaining -1. Okay, so LDIA flip run remaining add AD LDAA because we cannot subtract 1 unless we get to the value of remaining. So now A has remaining. We just have to decrement it by 1, decrement A. Then we push it on the stack, decrement D, stda. And now we need to push the address of n. So this time we're pushing the address of my local variable. So we have to do a LDIA flip run underscore n add AD, and that would be the address. Wait, we just push something else on the stack. In other words, the other thing you need to track is where is the stack pointer pointing. Every time you push something inside the function, you have to make a note. It's like, oh, wait, the stack pointer is not pointing at the base of the frame anymore. How far am I below the frame, the base of the frame? Because it depends on how many things you have pushed at that point. Okay, so this is also something that you can put on a checklist. Okay, things that you have to pay attention to, things that you have to do counting, things that you have to comment and go like, oh wait, the stack pointer is not pointing to the base of the frame anymore. Okay, all right. So that means, oh, okay, we have to remember to add 1 to it because the stack pointer is now pointing to 1 byte below the base of the frame. All right, but that would be the address of n already. I don't have to do a dereference. So now I just have to push it on the stack, push register A on the stack, stda, get it pushed. And now we have to push the return address, which is LDI A.6 plus, decrement D, stda. Now I can do an unconditional branch to the function. When it comes back, I have 2 arguments or 2 bytes of arguments to deallocate, increment D, and the return value is in register A already, which is also my return value register. So I don't have anything else to move around in this case. So I think that should implement the entire thing. All right. The question now is, but what does it actually do? Now, in the final exam, you don't have to worry about that, right? Because you're not going to be able to run the C code. You cannot run the assembly code. All you can do is to translate the code, okay? And make sure that whatever translation I gave you or I give you is correct and spot all the problems, fix all those problems. That's going to be your job. But in this case, if I need to check whether this program is actually working or not, then I have to observe, what it is doing to in the C code. So in the C code, let me check. Okay, so to look at the side effect of what it is doing, it's making changes to PV and also PN. So that means, to debug this code, I need to kind of look at, what it is doing, to um, the pointers. And I'm just trying to figure out, how to show the output or show the effect of the C code so that we can also check the effect of the assembly code and make sure they are the same. All right, so let me go back to the C code here. Okay, so all the changes are done on line 20 and line 21. And we can also look at the return value. The return value is going to return. So all the returns here are basically, one of the values. Um, so we can, the linked list is fully formed when we stop the recursion. In other words, for this branch and this branch over here, that is when the recursion ends, and that's the state that we need to check. So that's what we need to do in the C code, and we have to do the same thing in the assembly code, is to check that. Um, and we also have not implemented that last thing, because if you look at the to do, we still got one thing to do. Oh, not on this side here. All right, so let's finish the program in main. So we have flip run already implemented. We just have to store the return value +1 into, whatever this PV is. So let's go ahead and do that. All right, so let's do that. Increment A, because A is the return value of flip run. We're supposed to add one to it. So that will give me the entire right-hand side. The left-hand side is LDI B main underscore first, and then we need to access PV. So it'd be R underscore PV plus, and then add BD, and then STBA. All right, so that should finish the assembly code. And this is just the C code on this side. All right, so we'll see what this side is gonna say first, the C code side. So gcc-g-o fx.c gdbfx, run the program until we get to line 38, run it, and look at f first points to first dot pv, and compare that to the array A. Okay, so we have to look at the address of array A. All right, so it is pointing to the very beginning of the entire array, and that's the effect of running this in the C code. So now we have to run it in assembly code and see whether it is accomplishing the same thing. So this is a whole program. And I will be kind of surprised if it does even run, without any assemble time error. So we'll see. Okay, well, it did run, no assemble time error. So if I were to be more confident than I should be, I'll be going to the end of this trace, and that is not working. All right, good. I like it when it doesn't work. So why is it not working? It's not working because um, we have a stack problem. So let's look at the stack problem, okay? Because you might run into this problem when you're implementing your traverse program, is when your stack pointer is too low and it is, oh, I'm looking at the wrong tab anyway. Here's the right tab. Okay, so let's check. Oh, okay, it did terminate correctly, and it's storing 09 into FF. So when we go back to the map, location FF, oh, okay, that's not storing, that is retrieving. Excuse me. It's storing a 0, 1 into FE. And when we look at this part here, location FE is supposed to be storing um, the address of an element of array, and what it is storing is definitely not correct. So returning a 0, 1 is definitely not right. So now I have to go back and try to fix the program. So how do we fix the program? In any other class, you have GDB, you have a typical debugger. So that means you cannot execute a program backwards in those environments. But in this class, you can, because it gives you the entire trace. So that means I should be able to trace all the way back to find out where this 1 is coming from. Where do I get the return value of 1? So that's exactly what I'm going to do. Okay, this is incrementing 1, which means that before we increment 1, it was a 0. So somewhere along the line, somebody returned a 0. So that means I need to look up, who put a 0 into register A. It would be this line here. So this line is returning a 0 after it is decrementing A from the then branch of the else branch. So that means this A is incorrect. It is supposed to be the address of something, but it's not the address of something. All right, so we go back to line 49, which is the compare, and we're comparing A, B on line 49. So now I actually have to look at the code. All right, so we go back to line 49. Oops. All right, so by this time, register A has a 0 in it. It has a 1 in it. So that means by the time we get to else 0, then 0, I made the wrong assumption because it has not gone through this code yet. Okay, so I have found my bug. Okay, let me tell you what the bug was. It was a bad assumption on my part because I said, rather smugly and say, oh, I can just shortcut this whole thing because by the time I get here, register A is gonna have whatever PV is as a member of the structure that PPOS is pointing to, because I was only looking at this local code here. But guess what? There's another way to get to this point, bypassing this code. That was what I did not account for. Is that okay? Does everybody understand what I said? So I made a mistake. It was a very bad mistake that I made because I was trying to optimize the code, forgetting that to get to this branch over here, which is the label, else 0, else 0, there's another way to get here. The other way to get here was, mm, it was, okay, it was definitely this branch. So let me see in the trace how we got there. Okay, so we have to compare A, and then we go to else 0, then 0. It did perform the branch. Then we get to line 49. Okay, so we got to line 49. We have this J. Which branch did I use? I use a JZI. So the J, go ahead. Um, I took this branch. So by the time I took this branch on line 50, register A has a very simple constant of 1 in it. But when I got to the branch, when I got to the label of else 0, then 0, okay, I made the assumption that register A has the PV member plus 1 of the structure that PPOS points to. So that assumption was wrong because I have two places to get to. I have two ways to get to this particular label. The first way to get to this label does not put what I need into register A prior to getting here. So that means the assumption was wrong. Is that okay? Okay, let me see if I can display both conditional branches at the same time. Then you guys can see, oh, okay, so there are two ways to get there. This is the first conditional branch that can land me on that at that spot. This is the second one. The second one is not a problem because by the time I get to the JLI on line 63, register A, in fact, will have PPOS points to PV plus 1. That is not the problem. The problem is the first one because if I took the first branch here to get to the label else 0 then 0, which is the same place here, register A just has 1 in it. So that's why that is the reason why it didn't work. So that means I cannot really take that shortcut. I actually have to do the whole thing here. All right, fine, we'll do the whole thing, which is oh, okay, it's not that bad anyway. So we'll just go ahead and implement the whole thing. LDI register A with flip run underscore PPOS. In other words, I'm just going to line 17 and I'm just recomputing the entire return value without any assumption because I cannot make that assumption anymore. So we put the offset here, we get to the address, and then we get to the value. So now register A has PPOS, which is the address of a structure, LDIB with the offset to member PV of a structure. So that's R underscore PV, add register B to register A, and then dereference it once. Now it should be correct. All right, so we'll give it a test run and see if it does it correctly. All right, save the file and run it again. All right, so we go back to the assembler and skip all the way to the end because all I really care is what did I store into location, I guess it is FE because FE is PV. So it is storing, which location again? FC. So it's storing A bracket 2 or the address of A bracket 2 into PV over here, which is not what the C code is doing, I think. I'll double check. All right, so this is the C code. Oh, wait, the assignment is not done yet. I put a breakpoint on line 38, but it has not performed line 38 yet. So that means I need, where did I put a breakpoint? I put a breakpoint on line 38. I need to put a breakpoint on line 40 and then continue execution. Now we can test it. There we go. So first dot .pv is 7f, okay? And where is the address of A? It is 7D. So now you have to look at how many bytes are between the F and the D. So do some counting. D, E, F, 2, right? So that means we are looking at the assembly code and we want this to be 2 bytes after the beginning of the array A. And when we look at the map here, the array A starts at location FA. So 2 bytes after that is in fact FC. So now the code is behaving correctly. All right, so I know you guys are kind of drained right now, okay, because that's a lot of stuff. So the best way to process this is to focus on the techniques first, okay, not the details, because if you get to the details, it's a whole lot of pine needles and you can lose track, pretty quickly. So it's the techniques and what concepts are involved that are the most important. The details, you can always go back to watch the video again. I hope it's still being recorded. Yes, because I don't want to re-record this one. Okay, this is not one of those things I want to re-record. It is still being recorded. Okay, so the details you can always go back to the video and and just go to a certain segment and get the details. But it's the idea first. How are you guys along in the implementation of Traverse? Mm, okay, are you guys breaking it up into stages like what I suggested? Okay, have you gotten past like the first or the second stage? Working on it. Okay, very good. So I'm gonna stop the recording because I think this is you know the limit of what how much intensive stuff we can go through in a single setting. When I took assembly language programming, it was a Monday night only class. So it's a 3 hour class from 7 p.m. to 10 p.m. It was taught by a lecturer from UC Berkeley too. So they were talking about virtual memory, page faults, interrupts, and stuff like that. Let's just say that those are much more advanced topics compared to what we talk about in this class. Um, yep. But then again, we started off with 60 students in that class, and by the time we get to the final exam, there were 12 people left. Like 20% of people remained in the class. It's not like 20% of the people dropped the class. 20% of the people left, were remaining at the end of that class. So don't ask me what happened to the rest of the class. I have no idea. All right, so I'm stopping the recorder.